Depicted here is a Bohr model of an atom. While the Bohr model is not necessarily accurate, it is sufficient in showing how electrons occupy an atom. Electrons reside around the nucleus of an atom in specified energy levels. Energy levels are assigned numbers, n. The first energy level has an n equal to 1, and each subsequent number signifies the next energy level. Electrons in the inner shells are called core electrons, and outer electrons are called valence electrons. Each energy level has subshells that are also known as orbitals. There are 4 orbitals, s, p, d, and f. S orbitals can hold a maximum of 2 electrons, p orbitals can hold 6 electrons, d orbitals can hold 10 electrons, and f orbitals can hold 14 electrons. Pictured in the diagram are the possible probability clouds of electrons in orbitals. To indicate an orbital in a particular energy level, write the number of the energy level followed by the letter of the orbital. For example, the p orbital in the second energy levels is designated as 2p. Electron configuration represents the arrangement of electrons in an atom. There are 2 ways to find the electron configuration of an atom. The first way, or the dumb way, is using the diagram pictured here. You follow the arrows from the top left to the bottom right, writing down the orbitals until all of the electrons have been accounted for. This method is easy but does not explain much. The second method involves using a periodic table. In the periodic table pictured, a certain region corresponds with an orbital. To find the electron configuration of an atom, you count the total number of electrons in the atom and go from left to right and top to bottom of the table, where the first and second periodic groups are s orbitals, the last 6 groups are p orbitals, the transition metal area is the d orbitals, and the lanthanide and actinide metals are f orbitals.
There are 3 rules that electron configurations must follow. The Aufbau principle states that electrons are placed in orbitals, subshells, and shells in order of increasing energy. The Pauli exclusion principle states that 2 electrons which share an atom cannot have the same spin, or cannot have all 4 quantum numbers be the same. The Hund's rule states that when an electron is added to a subshell, it will always occupy an empty orbital if one is available. In the electron orbital diagram here, electrons are filled in the suborbitals following the 3 rules until all electrons are accommodated for. Ionization energy is the energy required to remove the most loosely bound valence electron in an atom. Depicted here is Coulomb's law. Coulomb's law tells us the energetic relationship between an electron and its nucleus. The closer an electron is to the nucleus, the higher the force, F. Coulombic attraction increases left to right on the periodic table due to the increase in effective nuclear charge. This makes the electron harder to remove, thus increasing ionization energy.
Inner electrons shield valence electrons from the nucleus and diminish the actual effective nuclear charge felt by the valence electrons. This is called electron shielding. The greater the shielding, the less attraction is felt by the valence electrons. Therefore, the electron shell has a lower Coulombic attraction and ionization energy. The location of an electron can be represented by 4 quantum numbers: n, l, m sub l, and m sub s. N, or the principal quantum number, is the energy level of the electron and can have integer values from 1 to infinity. L, or the angular momentum quantum number, represents the shape of the orbital. L can have values from 0 to n minus 1. For example, s orbitals have an L of O, p orbitals have an L of 1, and so on. M sub L, or the magnetic quantum number, describes the 3D orientation of the orbital. M sub L values are integers ranging from negative L to positive L. Finally, M sub S, or the spin quantum number, describes the magnetic field of an electron. 2 electrons in the same orbital cannot have the same spin energy. The spin quantum number can either be negative 1/2 or positive 1/2.
In this video, we showed how the electronic structure of an atom could be described using an electron configuration that reflects the concept of electrons in quantized energy levels or shells. Overall, the energetics of the electrons in the atom can be understood by consideration of Coulomb's law. Thanks for listening.